So we're working on optimization problems tonight.
Yes.
Okay. How much of this have you had? Is this relatively new for you, or have you had a lot?
No, we did it in the first semester.
Okay.
But it's one of the things I have had trouble with.
Okay. For sure.
And I do need it for my mathematics hours.
Yeah, for sure the two toughest parts of differentiation are optimization and related rates. Have you had related rates also?
Yes, I had that last year.
Also? Okay.
No, that was second semester of my sophomore year.
Oh, wow. Okay. Boy, they
So
learned you on calculus early, didn't they? I guess that's the IB.
Yes, they did have me on track for that.
That's the IB program, is they introduced calculus much earlier than everybody else. Okay. Well, let's hold on a second. Let's start out with a very basic one. And we'll see how you do, and I'll increase the level of difficulty depending on your understanding of it. Probably one of the most basic optimization problems you can get is a rancher has a house and he wants to build a corral. On the side of his house. And he has 2,000 feet of fencing available to him. What should the dimensions of X and Y be so that he optimizes or maximizes the area of that corral?
Okay.
In other words, this is a very real-life problem, one that lots of ranchers have faced and have had to figure this out. They may not have 2,000 feet of fencing, but they have some finite feet of fencing, and they want to build a corral out of it and figure out how to design the corral to get the maximum area. And it actually does require calculus. It's not... I don't think this is doable. Maybe it's doable by algebra. I don't know. But it's the most simplistic optimization problem for calculus.
Right.
So, do you know where to start?
Start with 2x plus y equals 2,000, since that's the fencing.
Okay.
And it wouldn't be 2y because one side of the house is...
You're absolutely right.
Taking care of it. And then I would need another equation.
Okay. The other equation is what I call the primary equation. It's the one you want to optimize. This equation is going to be useful, but it's not the primary equation. The primary equation is what? What's the area of that shape?
X times y.
Okay, good. We know that if we take the derivative of something and set it equal to 0, we will see where it's at maximums and where it's at minimums.
Right.
Well, the problem here is that we have an area function that is a function of two variables, x and y. So if we can turn it into a function of one variable only, then we'll be well on our way to being able to optimize it. Well, using this fencing criterion, we can solve for either x or y. Y.
Right, so let's start out with y equals 2,000 minus 2x. That way we have y on one side.
Okay. Now we can substitute that into the area function. So now we're going to have area strictly as a function of x, and it's going to be x times 2,000 minus 2x. So now we've accomplished our primary goal. We have our primary function, and it's a function of one variable only, and that's a key. Okay, so what now?
Distribute the x into 2,000 minus 2x.
Okay. What now?
Have a equals 0, so that way
Not
then
a.
you could
We want to take the derivative. In other words, what we're looking at
okay,
is
the
a
derivative.
quadratic. So it's going to look something like that. Okay.
Right. And then find the quadratic so that way you could find that.
We want to find that point right there. Where on the x-axis is the vertex of that thing? So we can actually use algebra here. But we'll get more progressively harder problems that will be cubics and quartics, in which case you can't use algebra and you have to use calculus. But let's use calculus here anyway. So the goal is we need to first take the first derivative. We need to find out what a prime of x is. What is that?
Okay. 2,000 minus 4x.
And now we're going to set that equal to 0 because we know in this function here it looks something like that. And the reason we set its first derivative to 0 is because that's what the slope of the tangent line is at that vertex. That's the only place on that function where the slope of the tangent line is 0. So if we set a prime of x equal to 0, we're going to find that maximum point. And we discover that x of 500,
Okay, yeah.
gives us our answer. In other words, this would be...
Okay, and then we can plug it back into the...
into that equation
x
right
plus
there.
y equals 2,000.
Right.
Right.
Plug in 500 for x and we get y of 1,000. You can actually go back and plug it into either equation. But so that's the basic strategy of optimization, is you identify a primary function that you want to optimize. It's usually of 2 or more variables. Use other information that allows you to turn it into a function of one variable. Take its first derivative, set it equal to 0, solve for the one variable. Using that value, you can solve for the second variable.
All right.
Okay?
Okay, but the problem that I have to do for my math IA is, see, what I'm doing is I'm trying to minimize, through optimization, the area of a shadow in accordance to a degree of the light.
Okay.
And I wanted to make sure that I could do that.
Okay. We can certainly tackle that problem. Let's hold off on that, and I've got a couple of others here that get progressively harder that I think it's worth. It's like if I was trying to teach you to ski on the expert slopes, I'd start you on the beginning and then go to the medium and then the experts. So I don't want to start off with too hard of a problem.
So the problem that I was speaking of, it's a little bit more difficult than the others.
Right. That first problem is about as easy as it gets. This is slightly different.
All right.
But illustrate.
But what would make the problem that I say more difficult?
Okay. We'll get to it. We have a parabola there that's defined by y equals 3 minus x squared. What's the biggest size rectangle we can fit inside that parabola? Notice that I could build my rectangle like that, or I could build it in any shape I want, but the goal is to get the maximum area.
Right.
Okay, so what's my primary function that I want to deal with? In other words, what's my function that I want to optimize?
You would want to optimize the area of the rectangle, so it'd be not x times y, z times w.
Actually, you were absolutely correct. It's x times y. In other words, regardless of regardless of where I put this rectangle, this dimension, it's 2x times y.
Okay,
In other words, regardless of where I draw that rectangle, the distance from here to here is x, which makes its base 2x. Its height is that dimension or that dimension, and that is y. So the area function is 2x times y. Well, I know what y is, right?
Right.
In other words, the y measurement is that parabola, which is 3 minus x squared. So now my area function becomes a cubic, which I would not be able to solve with algebra.
But you could pull out you would find the derivative, right?
Right. In other words, my area function as a function of x alone is that 6x minus 2x cubed.
Right.
Now, if all you were dealing with was algebra, you wouldn't be able to find the vertex of this. In the last problem, we had a quadratic. And, you could have used algebraic techniques to find the vertex of that quadratic. But when you have a cubic, now we really can only take the first derivative of this, set it equal to 0. That's going to give us two places, one of which will be a maximum, one of which will be a minimum.
Right.
So a prime of x is equal to 6 minus 6x squared. Setting that equal to 0, I get x squared equals 1. So x equal plus or minus 1.
Okay.
Well, it doesn't make any sense to have a minus, so we take the plus answer. So where x is equal to 1,
2?
Well, x is equal to 1. And the y coordinate...
Right. I was talking about y.
Right. Y is equal to 2. So, in other words, the rectangle that produces the maximum area is one where this is 1. And the y coordinate for that would be 2. And that produces an area of 4 for that particular rectangle. And you can't put a rectangle in there that's a bigger area. Okay? All right. Let's have your problem.
Okay.
Okay. So you have a light on a pole, presumably?
Yeah.
Okay. And there's something else out here that's going to produce a shadow. What? Is it another pole?
A
person?
For mine, I did a flashlight from a fixed radius onto a cube. So that way I could measure the shadow accurately.
So here's the flashlight. Is that an accurate depiction?
I had it at a at a fixed radius from the cube, so that way
Fixed
I wouldn't have to
radius
deal
from
with
the center of the cube?
Yes.
So we'll make that distance what?
1 foot.
Okay.
Since I didn't have a meter stick.
Okay. And clearly that light is going to hit this edge and produce a shadow of some distance.
Right.
Kind of like that. And
right.
Your object is to minimize the shadow. If I call that x, we want to minimize x?
Yes.
Okay, and what's our variable? Oops, hold on. The only variable I could see would be repositioning the flashlight. Obviously,
yes.
if the flashlight were right there, that would minimize our shadow, right? We would have zero shadow. Flashlight would shine light down.
Yes.
Ah, I see. But then we would have shadow over there.
Yes.
Okay, now I'm understanding the problem. And clearly the positioning I have really isn't. Let's redraw this. I'm close. I'm going to put the flashlight directly over the cube. Do we know the dimensions on the cube?
2 inch by 2 inch by 2 inch.
Is it 1 foot to the top of the cube or to the center?
To the center.
Okay.
So technically 10 inches away from the edge of the cube, but...
Actually, it looks like it would be 11 inches.
Well, yeah,
Because
11
if
inches.
it's a 2-inch cube, it's only going to be 1 inch from the center to this edge.
Right.
Okay.
But I tried to make it as simple as I could.
Right. Let me redraw this a little bit here.
So that way I wouldn't have to deal with experimental variables.
I can tell you what the answer is before I solve it. It's going to be dead over the center of that thing. At least I would bet.
Right, but I have to show it mathematically. I mean,
No, that's fine. No, we'll do that.
Yeah, I know theoretically that it would be right above. Mm-hmm. Yeah.
All right. If I lay this out on there, flashlight being there, cube being here, and the shadow, man, I wish I could, I apologize for being a horrible artist, but I don't know if
no, it's fine. I'm dreadful.
It's not easy to draw a straight line sometimes for me. This is actually similar to my previous problem, I believe.
Yes, it is.
Because the key this is 1 inch right here.
Right.
This is 1 minus x. In other words, if this is x, then that little tiny area is 1 minus x.
Right.
Okay? Let me think about this for a moment. We'll just analyze the right side only of this.
Okay.
Okay. This is 13 inches to the bottom of the cube. So, if let's see, if that little tiny area is 1 minus x, so if I make a distance function for the size of the shadow,
right,
if I were to put the flashlight over here, it would create no shadow on one side, but a bigger shadow on the other. But the shadow length is still going to be 1 minus x thinking for a moment here. Let's see, that...
Wait, sorry, hold on.
Go ahead.
Wait, why is it 13 inches?
Well, if this represents the entire cube, and it was 12 inches to the center, and the center is an inch from the bottom.
Oh, right.
So it'd be
Okay.
13 inches. So let's see. We have a triangle. If the flashlight's directly above the cube, then this triangle is 13 by x. And our shadow length function, let's call it length, is equal to 1 minus x times 2 if it's in the middle of the cube, but times just 1 minus x if it's on one end of the cube or another.
Okay.
Let's see. If I let, if this distance here, in other words, if my answer is some distance from the vertical over the center of the cube, then that's what I'm wanting to solve for.
Right.
But that distance is, because we have parallel lines, that's the same as this distance here.
Yeah.
Hold on a minute. I still got to think about this for a second. Let's look at the two possible triangles here. Maybe that'll enlighten me.
Okay.
In other words, if the flashlight is in this position here, directly over the left edge of the cube, then it only produces one shadow.
Right.
And that would be, hold on. That shadow. If the flashlight is directly over the center of the cube, then it produces two shadows. The question is, which is the smaller total distance, correct?
Correct.
Okay. Let's see. In this triangle here, that's 13. Oh, actually, yeah, this is, no, you know what? This is not a straight line. Since that's a radius to the center, that's a curved line that I can move that flashlight, correct?
Yeah. Yes.
Okay, so this
Which
triangle,
is partial.
this triangle here means that that side's not 13. And this triangle here, it means that the vertical is 13.
Right.
And in this triangle here, we know that it is 12 to there. And this is 12 to there.
Yes. Out of curiosity, would this problem be easier if it was just 12 inches from
the top?
From the...
I don't think so. I think actually being 12 inches from the center is going to make it easier. Notice how much harder it would be if it was 12 inches from the top. That means this distance, that actually might make it easier. That would be 12 inches, and that would be 12 inches. This problem, let's see. If we draw another triangle there, now 12 is the hypotenuse. This is 1. And this distance here would be the square root of 143.
Right.
This is 2. This is 1. So this distance of the shadow is it's x minus 2. In other words, this measurement right there should be x minus 2. And this measurement here of the shadow length is x minus 1. I said 1 minus x, didn't I? It should be x minus 1.
Yeah.
Where does that leave us? We must have to be dealing with an angle here.
Yes.
In other words, this angle right here of theta determines where that flashlight is placed. It's either 0 degrees if the flashlight is directly above the cube, or it's whatever this angle is, and I could calculate it by using the triangles to figure out what theta would be from the vertical in this diagram here. trying to figure out our shadow length in both pictures. Theta is the variable. Because it is a certain radius from the center of the cube, then the only thing that varies here is this angle theta. From this picture over here.
Right.
And that theta is the same
you're slightly misunderstanding.
That theta. What's that?
I think you're slightly misunderstanding of the problem that I have.
Okay.
See, I do have, well, more accurately, I will have the actual areas of the shadows. I would just have to optimize the angle in which it is. Like, I can see the general trend.
Right. So they give you the area.
Like, seeing it from a graphing, but like seeing it from a graphing point.
Oh, I get it. And you're minimizing the area of the shadow, not just the length. And the reason it's an area is because we have a cube here, not a square. And so it would give an area of a shadow. Yeah.
Right.
And the answer is going to be a certain theta that gives the area of that shadow. Well, let's see. We can use a trig function here. And have you had derivatives of trig functions?
Yes.
Okay. I feel like that's going to be our solution, is setting up a trig function, probably tangent of theta.
Okay.
I'm not sure I can do this in the amount of time we have left here. I'll give it a shot at just kind of thinking through it on the fly. The tangent of theta is going to be x divided where does this thing cross that y-axis? At y? Tangent of theta is going to be x over y of that triangle. I don't know, Diana. I may have to think about this longer than I have time for now.
Right.
And we can certainly address this at our next session. I'll work on it and see if I can come to a little better understanding of it. I think I can probably work it out, and we'll end up with the area of the shadow function being a function of theta instead of x or y. Okay? If we can get the area of the shadow to be a function of theta, then we can differentiate it, set it equal to 0, and solve for what theta gives us that maximum area function.
Right, and also next session I will actually have the actual data.
Okay, so tell me what other inference. So you have the area of the shadow, and that might be necessary. That may be one reason I can't make. So let's make one up. The area of the shadow, well, no, we can't do that, can we? Because it is a certain area. So you're saying the minimum area of the shadow is some number, and we have to figure out what theta is to produce that number. Okay.
Yes.
I think I can kind of make more progress on it now. Okay. Yeah. So we'll have this number here. And I can figure out what the area of the shadow is. The area of the shadow is going to be 2 inches times x minus 1 here, that quantity times 2. Or if it's this configuration, it's a different area. It's just x minus 2. I may have to think about that a little bit longer. But yeah.
Okay, since also, once I get the information, I can text you.
Yeah, if you would, that would be helpful. Once you get the whole problem, go ahead and take a picture of it and send it to me in advance. And anytime you have a...
yes, once I get the entire...
Yeah. Incidentally, the last time, remember when I had a problem with the resolution? After our session, I looked at my email, and I found the second email you sent me, and it was much, much better. So whatever you did, you fixed it. Okay. Or whatever your mother suggested you do, I don't know. In fact, if you could figure out what it is, I would be interested in knowing, because so I can tell my other iPhone students that have the same problem. Since I don't have an iPhone, I don't know, the software that well for the iPhone.
Okay, you see what I did, I took the normal picture, and then I attached it, and I set it to the largest setting, so that way it would send it in the best quality.
Okay, so you didn't set it before you took the picture, and that's why your resolution looked perfect on your camera. Okay, so that's the secret, is when you attach it as a file.
When I transferred it to an email, the size of the document matters. You have to set it to
maximum.
The largest one.
Right. Okay, I get it. Okay. Yeah, mine, I don't know that mine works that way. I've never really tried to do that, so I don't know. My Samsung.
You see, it only comes up when you're texting it or when you're emailing it, but when you're actually taking the photo, it doesn't come up.
Right, I can see that.
Only when you're attaching it to a document or something.
And I'm sure your defaults on that phone were the highest resolution possible on your photographs.
Yes, but it's just
yeah.
It's not about the resolution.
It's about
how high of a setting you're setting it.
Because you can take a picture that's too big for the email or the texting, so it'll adjust the resolution to let you make it as big as possible based on that file size. So yeah, okay, I understand how it works now. Yeah, well, if you can text this problem to me or email it to me before our session, maybe a half hour before at least, give me a chance to look at it a little bit more. I think I can get to the bottom of it. Okay, all right, Diana. Let's see. Are we going to still do Thursdays? I assume you're in that play since you had rehearsal on Thursday?
Oh, the concert that we had was on Friday, so it was only for that week.
Okay. So Thursday at 6 is going to be our regular time for next week. Sounds good. I'll talk to you then.
All right, bye.
Bye-bye.